You probably think Copilot's biggest flaw is the license price. But in reality, the license is the smallest part of the problem. The real issue is what's behind every Copilot request. A frontier model that costs too much, responds too slowly, and processes your data in jurisdictions you don't control. There's a better architecture, and it starts with thinking smaller. The broken assumption: bigger is better. Your organization didn't set out to over-engineer its AI strategy. You wanted Copilot because it promised to make your teams faster, your decisions sharper, and your workflows smarter. So you bought the licenses, enabled the features, and started routing every request through the most capable model Microsoft offered. That felt like the right move because in 2023, bigger really was better. GPT-4 could do things that smaller models couldn't touch, and the gap was so wide that choosing anything else felt like settling. But in reality, that assumption has become a structural flaw. Enterprise AI in 2026 isn't a research lab where every task demands frontier-level reasoning. It's a production environment where thousands of employees are doing the same narrow tasks repeatedly. They're summarizing email threads, they're extracting action items from meetings, they're classifying documents, drafting replies, and searching through SharePoint. These tasks don't need a trillion-parameter model that can write poetry and debug code. They need a model that can do the specific job quickly, cheaply, and without sending your data on a round trip through a data center you don't own. The research points to a clear shift in how Microsoft itself is architecting Copilot. The company reorganized its Copilot division in March 2026, moving consumer and commercial Copilot under a single organization with a mandate to build tiered capabilities. The memo from Satya Nadella explicitly tied model development to product benchmarks and serving costs. Microsoft isn't betting on one massive model anymore. It's building a portfolio where different model sizes serve different tiers of user need. That should tell you something. The company that built Copilot around OpenAI's largest models is now actively working to reduce its dependence on them, not because the big models are bad, but because using them for everything is architecturally wrong. It's like deploying a mainframe to run a spreadsheet. The compute is real and the capability is undeniable, but the fit is broken. And the cost of that broken fit isn't just theoretical. It shows up in 3 places that every IT leader and architect can measure. The first is money, the second is time, and the third is control. Let's talk about what each one is actually costing you. The cognitive dissonance here is worth naming explicitly. Most organizations know their AI spending is growing. They see the monthly Azure bill. They track the Copilot license costs, but they don't connect the individual click to the cumulative meter. An employee in Outlook hits summarize this thread without thinking about the tokens. A manager in Teams asks for a meeting recap without considering the inference cost. A finance analyst requests a formula explanation without realizing it just triggered a premium model call. These micro decisions, repeated thousands of times across hundreds of users, aggregate into macro spending that no one budgeted for. And because the spending is metered rather than fixed, it's unpredictable. Your Copilot usage in March might be double your usage in February because of a product launch, a compliance deadline, or a seasonal peak. The finance team can't forecast it, the procurement team can't negotiate it, and the IT team finds itself in the uncomfortable position of explaining why a $30 per user license turned into a 6-figure annual variable cost that wasn't on anyone's roadmap. This is the structural flaw in action. It is not a bug in Copilot, and it is not a pricing trick by Microsoft. Just an architectural mismatch between a general-purpose supermodel and a narrow-purpose production workload. And that mismatch is what small language models are specifically engineered to solve. The cost reality, the Copilot tax. Most organizations think about Copilot cost as a per-seat license. You pay $30 per user per month, and that's your AI budget. But in reality, that's only the entry fee. The real cost is what happens every time one of your employees clicks the Copilot button. Every request hits a large language model. Every token of input and output is metered. And when you're running a frontier model like GPT-4o at enterprise scale, those tokens add up faster than most finance teams realize. Research on enterprise AI workloads shows that GPT-4o runs at roughly $4 to $5 per million tokens on a blended basis. That sounds small until you multiply it by thousands of users, making dozens of requests every single day. A single team of 50 people, each using Copilot for routine drafting and summarization, can burn through millions of tokens in a month without anyone noticing. Now compare that to small language models. Phi 3.5 Mini, one of Microsoft's own SLMs, runs at about 10 cents per million tokens. That's not a minor discount. That's a 300 times difference on input costs and a 600 times difference on output. For high volume, low complexity tasks, the exact tasks that make up 80% of daily Copilot usage, that gap turns a manageable line item into a budget crisis. The research on enterprise cost analysis puts this in stark terms. Organizations running hybrid architectures, where SLMs handle routine traffic and frontier models stay in reserve for complex cases, are seeing 5 to 7 times annual cost reductions compared to LLM-first designs. Some specific workloads report per-inference savings of 10 to 100 times. And when you self-host an SLM on your own infrastructure, the economics get even sharper. The break-even period for on-premise small models is measured in months, not years. Here's why this matters for your Copilot strategy specifically. Microsoft 365 Copilot isn't one feature. It's dozens of features embedded across Outlook, Teams, Word, Excel, and SharePoint. Every summarized email thread is a request. Every meeting recap is a request. Every draft reply, every document query, every data extraction, they're all requests. If every single one of them hits a frontier model, you're paying premium prices for basic tasks. The smart enterprises aren't debating whether to keep Copilot. They're debating which model should power each part of it. And the answer for the bulk of daily work is not the biggest one. Consider what this means at scale. A mid-sized enterprise with 2,000 Copilot users might generate 20 million tokens per month on routine tasks alone. At GPT-4o blended rates, that's $80,000 to $100,000 in inference costs annually on top of license fees. At Phi 3.5 mini rates, it's $2,000. The difference, $78,000 to $98,000 per year for a single mid-sized deployment, is more than enough to fund a dedicated AI infrastructure engineer, a local GPU server, and the operational tooling to manage a hybrid architecture. And that's before you factor in the latency improvements, the sovereignty benefits, and the user adoption gains that come with faster, more responsive tools. The research on enterprise cost analysis puts the break-even math in even sharper terms. Organizations processing at least 50 million tokens per month see break-even periods for on-premise small models measured in months rather than years. At that volume, the capital expenditure of a local server pays for itself in under 2 quarters compared to cloud API consumption. For organizations already operating Azure Local or on-premise Kubernetes clusters, the incremental cost of adding an SLM workload is often just the GPU allocation and the operator time. The infrastructure is already there. This is why the per-seat license framing is so misleading. It treats Copilot as a fixed-cost software product like Office or Teams, but the AI layer underneath is a variable cost utility like electricity or bandwidth. And just as smart organizations negotiate bandwidth contracts and optimize compute utilization, smart organizations now need to optimize their model utilization. The license gets you access. The model selection determines what that access actually costs. The latency problem, waiting for intelligence. Cost hurts your budget, latency hurts your users, and when users stop trusting a tool because it's too slow, the ROI collapses regardless of what you paid for it. A cloud-hosted frontier model doesn't just cost more per token, it takes longer to respond. Research on Azure AI task latency shows that GPT-4 class models typically deliver first token latency in the range of 300 to 2,000 milliseconds, depending on load, region, and context length. That's before the model even starts generating useful output. Then you wait for the full response to stream back. For a user writing a quick email draft, 2 seconds feels like an eternity. For a Teams meeting that needs real-time summarization, it's unusable. And for workflows that require multiple model calls in sequence, classify this document, extract these fields, draft this summary, route it to the right person, the delays multiply. What looks like a small per-request lag becomes a systemic productivity drain. Small language models change this equation completely. When deployed on edge hardware or local infrastructure, SLMs like Phi 3 Mini can deliver first responses in 10 to 50 milliseconds. On a modest GPU, they generate over 12 tokens per second. On a phone or laptop, quantized versions still run fast enough to feel instant. The research makes the comparison explicit. SLMs respond in 10 to 50 milliseconds on edge deployments, while cloud LLMs take 300 to 2,000 milliseconds for first token latency. That gap isn't a minor optimization. It's the difference between a tool that feels like part of your workflow and a tool that feels like a bottleneck. Microsoft's own documentation frames this as a core reason to adopt SLMs. They describe small models as essential for scenarios where limited computing power, low latency, or keeping costs down is critical. The company isn't positioning SLMs as a budget alternative for small businesses. It's positioning them as the right architecture for high-frequency enterprise tasks. And here's the part most organizations miss. Latency isn't just a user experience problem, it's an adoption problem. If your employees try Copilot twice, wait 2 seconds each time, and decide it's faster to just do the work themselves, they won't come back. The license is paid and the feature is enabled, but the behavior doesn't stick. And the ROI you promised your board never materializes. The psychology of tool adoption follows a predictable curve. Early adopters tolerate friction because they're motivated by novelty and status. They'll wait 3 seconds for a meeting summary because they want to be the person who uses AI at work. But the broader employee base, the people who actually determine whether a deployment succeeds or fails, has a much shorter tolerance. If the tool doesn't save them time immediately, they abandon it. And once abandonment becomes the norm, the tool dies by disuse even though the monthly invoice keeps arriving. Microsoft's own research into Copilot adoption patterns confirms this. The most successful deployments aren't the ones with the most features enabled. They're the ones where users formed habits around a small set of high-value, low-friction tasks. Email summarization that happens instantly, draft replies that appear while they're still reading the thread, meeting recaps that are ready before they leave the conference room. These moments create the behavioral loop that sustains adoption, and these moments are exactly where SLMs excel, because their speed makes the interaction feel seamless rather than burdensome. The contrast becomes even more stark when you consider mobile and field workers. A sales representative checking a customer account on a tablet between meetings doesn't have the patience for a 2-second cloud round trip. A warehouse supervisor asking for inventory analysis on a handheld device needs the answer before the next truck arrives. A field technician troubleshooting equipment in a basement with spotty cellular coverage can't depend on cloud inference at all. For these users, local SLM deployment isn't an optimization. It's the difference between a tool that works and a tool that doesn't. Then there's the third problem, the one that doesn't show up in usage metrics or cost reports until it's already a crisis. The sovereignty gap, where your data actually goes. You probably assume that when your employee asks Copilot to summarize a contract in Word, the document stays in your tenant. The processing happens in Microsoft's cloud, sure, but within your EU data center under your compliance regime, governed by your controls. That's the enterprise data protection promise, but in reality, it's more complicated than that. In 2026, Microsoft introduced something called Copilot Flex Routing. It's a feature that allows LLM inferencing to be processed outside the EU when regional capacity is constrained. For new tenants, it's been enabled by default since March 2026. And as of April 2026, Microsoft turned it on by default for all EU and EFTA tenants, unless administrators explicitly disabled it. When Flex Routing activates, your Copilot requests can be processed in data centers in the United States, Canada, or Australia. Microsoft states that customer data at rest remains in the EU and that data is encrypted in transit. But the processing itself, the actual inference where your document content is fed into the model, happens outside your jurisdiction. If you're in a regulated industry, that distinction matters. Your data protection officer didn't sign off on EU data sitting in EU storage while being processed in a US facility. The legal basis for that transfer isn't automatic. It requires updated records of processing activities, transfer impact assessments, and a documented risk decision. And if your national regulator takes the view that processing equals data transfer, you're in breach. But Flex Routing isn't the only gap. Some Copilot capabilities now call Anthropic's Claude models. Those models are hosted on AWS infrastructure in the United States. When they're used, your data leaves the EU regardless of your Flex Routing settings. Microsoft's enterprise data protections still apply. No training on your data, encryption in transit, but the processing location is non-negotiable. Anthropic models are turned off by default for EU organizations, but admins can enable them. And some features do. Then there's Bing-connected web search inside Copilot. Those queries route through services outside your tenant, typically US-hosted. Microsoft says search queries aren't stored or used to profile your tenant, but for organizations under strict data minimization rules, trust us isn't a compliance strategy. The EU data boundary was supposed to solve this. Microsoft committed that personal data for EU customers would be stored and processed within the EU or EFTA with limited exceptions. And the company is rolling out in-country inferencing for Copilot in 15 countries by the end of 2026, including regional inferencing for the EU. But Flex Routing remains an available switch. Anthropic remains an optional model. And the boundary between compliant processing and cross-border inference is now a configuration checkbox that your admin either disabled or didn't know existed. This is what I mean by the sovereignty gap. You bought Copilot for productivity. You got a compliance surface area that expands every time Microsoft adds a new model or a new routing option. And the default settings are increasingly permissive, not restrictive. The complexity deepens when you look at the full configuration matrix that an administrator needs to manage. Flex Routing on or off, Anthropic models allowed or blocked. Bing Web Search integration enabled or disabled, tenant-level settings versus workload-specific settings, user group policies versus department-level exceptions. Each toggle represents a compliance decision that your data protection officer probably wasn't consulted on. And each toggle's default setting, as of 2026, leans toward functionality rather than restriction. For organizations in sectors like healthcare, finance, defense, and critical infrastructure, this isn't a minor administrative inconvenience. It's a potential breach of statutory obligation. National data localization laws may explicitly prohibit processing of citizen data outside national borders, regardless of encryption or contractual safeguards. Sectoral regulators like the European Banking Authority or national health privacy bodies may interpret inference processing as a reportable international transfer. And the Schrems II decision and its subsequent enforcement actions have made European data protection authorities increasingly skeptical of standard contractual clauses as a blanket justification for US-linked processing. The Microsoft EU data boundary is a genuine and substantial investment. The company has built regional data centers, implemented encryption, and published detailed documentation about what stays in the EU and what doesn't. But the boundary is not a force field. It's a configuration, and configurations can be changed by product updates, capacity constraints, or new feature rollouts that your organization didn't anticipate when it first signed the agreement. This is why the sovereignty conversation can't end with Microsoft says it's compliant. It has to extend to Can we verify and enforce compliance ourselves? And that requirement pushes the architecture toward local deployment, where the data doesn't leave your facility because the model is running inside your facility. No flex routing toggle matters when there is no route. No Anthropic model location matters when you're not calling Anthropic. No Bing web search leakage matters when the search layer is disabled or replaced with local retrieval. The sovereignty gap is the hardest of the three flaws to measure because its cost isn't a line item. It's a risk. It's the risk of a regulatory fine that could reach 4% of global revenue under GDPR. It's the risk of losing a government contract because your AI processing can't meet national security requirements. It's the risk of a reputational crisis when a journalist discovers that your EU customer data was processed in a US data center during a capacity peak. These are existential risks for some organizations, and they're entirely avoidable with the right architecture. So that's the flaw. Cost that scales unpredictably because every task hits a premium model. Latency that erodes adoption because users won't wait. And sovereignty that depends on admin toggles most organizations haven't reviewed since deployment. The fix isn't a bigger license or more cloud capacity. It's a different model architecture entirely, and that's where small language models come in. What is an SLM really? Small language models are exactly what the name suggests. They're language models with fewer parameters and simpler architectures than the frontier models that dominate the headlines. Where GPT-4 and its competitors operate at scales measured in hundreds of billions or even trillions of parameters, SLMs typically range from roughly 100 million to 7 billion parameters. That size difference isn't just a technical detail. It determines where the model can run, how fast it responds, what it costs to operate, and who controls the hardware it runs on. Microsoft defines SLMs as models built for efficiency and low resource use. They perform many of the same natural language tasks as their larger cousins: summarization, classification, drafting, extraction, translation, but they're optimized for scenarios where speed, cost, or deployment flexibility matters more than broad general knowledge. A 3 billion parameter model doesn't know as much trivia as a 1 trillion parameter model. But if your task is extracting action items from a Teams transcript, the model doesn't need to know who won the World Cup in 1986. It needs to understand meeting structure, identify tasks, assign owners, and format the output. That's a narrow job, and narrow jobs are what SLMs are built for. The architectural difference goes deeper than parameter count. Frontier models are designed to be generalists. They're trained on enormous, diverse datasets so they can handle almost any prompt you throw at them. That generality is their superpower and their weakness. It means they carry enormous amounts of knowledge you'll never use. It means they require multi-GPU clusters to serve at reasonable speed. And it means every request, no matter how simple, activates the full model. SLMs take a different approach. They're smaller, which means they can run on a single GPU, a modest server, or even a modern laptop. They can be fine-tuned quickly on domain-specific data because training a 3 billion parameter model is vastly cheaper and faster than training a 100 billion parameter model. And their narrow focus means they're often more predictable. They hallucinate less on tasks they've been trained for because there's less extraneous knowledge competing with the specific patterns they need to recognize. This is the fundamental reframe that most enterprise teams miss. They evaluate SLMs by asking whether a small model can do everything a large model can do. That's the wrong question. The right question is whether a small model can do the specific tasks you actually need and whether it can do them faster, cheaper, and closer to your data. The research on SLM architecture makes this distinction explicit. Small models are particularly effective when fine-tuned for specific narrow domains or tasks. They offer lower cost, faster response, and reduced energy consumption, and they can run on edge devices or constrained compute environments where a frontier model simply wouldn't fit. Microsoft's own documentation positions SLMs as the practical alternative where efficiency and device local deployment matter. For Microsoft 365 environments, this capability profile maps almost perfectly to the daily work stream. Summarizing an email thread is a bounded task. The model reads the thread, identifies key points, and produces a short summary. It doesn't need to know the history of email protocols or the cultural significance of the subject line. It just needs to extract information from a document you already have. Classification is even simpler. Is this document a contract, a memo, or an invoice? A small model can make that determination with high accuracy because the patterns are consistent and the context is local. The shift from one model to a model portfolio is what Microsoft itself is pursuing. The company's roadmap documents describe a hybrid AI approach where cloud-hosted Copilot handles large-scale reasoning and smaller task-specific models run closer to the user for speed, privacy, and offline resilience. This isn't a fringe experiment, it's the stated direction of the platform you're already paying for. There's a practical dimension to this that often gets lost in benchmark discussions. When you deploy an SLM, you're not just getting a cheaper model. You're getting a model that can be fine-tuned on your own data without requiring a cluster of A100 GPUs and a team of research scientists. A 3 billion parameter model can be fine-tuned on a single consumer-grade GPU in hours, not days. That means your organization's specific terminology, your document templates, your compliance language, and your brand voice can be embedded into the model without a six-figure training budget. The frontier models you access through APIs can't be fine-tuned in this way. You get what Microsoft or OpenAI built, adapted through prompting and retrieval, but never truly customized to your organization's specific patterns. This customizability has security implications too. When you run an SLM locally, you control the model weights, the inference code, the logging, and the update cadence. You don't depend on a vendor's moderation layer or their interpretation of safety guidelines. You can implement your own content filters, your own data loss prevention, and your own audit trails. For organizations in regulated industries that have been burned by cloud provider policy changes, this control isn't paranoia, it's operational necessity. And that brings us to the most important family of SLMs in the Microsoft ecosystem, the models that are specifically designed to make this hybrid architecture real. The Phi family deep dive. Microsoft's Phi family of small language models is the clearest evidence that the company is serious about this shift. These aren't third-party models that happen to work on Azure. They're built by Microsoft Research, optimized for Microsoft's own platforms, and positioned as the default choice for cost-sensitive and latency-critical workloads inside the Microsoft ecosystem. The current generation starts with Phi 3 Mini. It has roughly 3.8 billion parameters and was trained on 3.3 trillion tokens. That training scale relative to its size is part of why it punches above its weight. Microsoft didn't just shrink a large model, they trained a small model with the same data quality and curriculum techniques that make large models capable. The result is a model that, according to Microsoft's technical reports, achieves 69% on the massive multitask language understanding benchmark and scores 8.38 on the MT bench evaluation for instruction following and conversational quality. Those numbers put it in the same tier as GPT 3.5 class models, despite being small enough to run on a phone. Then there's Phi 3 small at roughly 7 billion parameters and Phi 3 medium at roughly 14 billion. As the parameter count increases, the capability increases predictably. Phi 3 small reaches 75% on MMLU and 8.7 on MT bench. Phi 3 medium hits 78% and 8.9. Microsoft reports that Phi 3 small and medium outperform same-class competitors like Llama 3 at similar sizes and approach the performance of much larger models on specific benchmarks. The later Phi 3.5 variants extend this line further. Phi 3.5 Mini improves multilingual capability significantly, jumping from 47.3 to 55.4 on multilingual MMLU. Phi 3.5 MOE uses a mixture of experts architecture with 16 sets of 3.8 billion parameters, activating roughly 6.6 billion parameters per forward pass. This design delivers performance that Microsoft describes as reaching above 90% of GPT-4o Mini's average performance across language benchmarks, while outperforming similarly sized open-source models like Llama 3.1 and Mixtral. There's also Phi 3 Vision, a 4.2 billion parameter multimodal model that can read and reason over images, charts, diagrams, and text within images. For M365 workloads, this matters more than it might seem at first. Excel screenshots, PowerPoint slides, scanned PDFs, whiteboard photos. These are everyday artifacts in enterprise work. A model that can interpret a chart from an image and summarize it in text is doing real work, not demonstrating a party trick. What makes the Phi family particularly relevant for Copilot isn't just the benchmark scores, it's the deployment profile. These models are designed to run efficiently on phones, laptops, and edge devices. They're available through Azure AI Studio and Azure Machine Learning with simplified deployment, scaling, and monitoring. And Microsoft explicitly markets them as the most capable and cost-effective models in their size class, outperforming models of the same or next size up on key benchmarks. This is the model portfolio that Microsoft wants you to use for the bulk of your AI workloads. Not because the company has given up on large models, but because Microsoft recognizes what the research confirms. Different tasks need different tools, and most enterprise tasks don't need the biggest tool in the box. It's worth pausing on the training methodology because it explains why Phi punches above its weight. Microsoft Research didn't simply compress a large model into a smaller one, which is the naive approach that usually produces mediocre small models. Instead, they used what they called textbook quality training data, carefully curated, high-quality synthetic datasets designed to teach reasoning patterns rather than memorization. The result is a model that learned how to think from a compact, well-structured curriculum rather than one that tried to memorize the entire internet. This pedagogical approach is why a 3.8 billion parameter model can rival a 175 billion parameter model on reasoning tasks, even though it would lose badly on trivia. For enterprise architects, this training philosophy has practical implications. A model trained on structured, high-quality data is often more predictable than one trained on massive, noisy datasets. It hallucinates less on routine tasks because it learned patterns rather than facts. It follows instructions more precisely because its training emphasized compliance with explicit prompts. And it's easier to fine-tune because the base model hasn't been saturated with conflicting information from the open web. But capability claims are easy. Let's look at the actual numbers, because the benchmark story is more nuanced than a simple win-loss record. Benchmarks, when 3.8 billion parameters outperform GPT-4. Comparing Phi-3 to GPT-4 isn't a simple question of which model is better. It's a question of which model is better for which task. And on the tasks that make up the majority of Microsoft 365 work, the small model is often the right choice. Let's start with the academic benchmarks. On the MMLU test, which measures broad knowledge across dozens of subjects, GPT-4 class models score well above 80%, Phi-3 mini scores 69%. That's a meaningful gap, and it reflects the fundamental trade-off of small models. They don't store as much factual knowledge. Microsoft acknowledges this explicitly in their technical reports, noting that Phi-3's limited parameter capacity shows up as weaker performance on knowledge-intensive tasks like trivia QA. But here's the critical insight for enterprise AI. Most M365 tasks aren't knowledge quizzes. They're reasoning tasks over content the user already has. When Copilot summarizes a meeting transcript, the model doesn't need to know world history. It needs to understand the structure of conversation, identify decisions, extract action items, and attribute them to participants. That's an instruction following and summarization task, not a general knowledge task. And on those tasks, the gap closes dramatically. On MT Bench, which measures conversational quality and instruction following, Phi-3 mini scores 8.38. That's firmly in GPT 3.5 territory. For the email drafting, reply generation, and document summarization that makes up the bulk of daily Copilot usage, that level of performance is sufficient. The model can follow your formatting preferences, adopt your tone, and produce coherent output. It might not win a trivia contest against GPT-4, but that's not the job. The Phi 3.5 MOE variant pushes even further. With its mixture of experts design, it reaches above 90% of GPT-4o Mini's average performance on language benchmarks. In some specific areas, like the math benchmark for mathematical reasoning, Phi 3.5 Mini actually beats GPT-4 in certain aggregations. For Excel formula generation, data explanation, and numerical analysis, tasks where Copilot is increasingly used, this matters. The multimodal story is equally relevant. Phi-3 Vision handles charts, diagrams, and text and images with competence that Microsoft describes as competitive or superior to comparable scale models. In the Phi-3 technical report, the company highlights that safety post-training significantly improves responsible AI performance across vision language benchmarks. For an enterprise deploying AI that will read screenshots of dashboards, scan invoices, and interpret presentation slides, this isn't a novelty. It's a core requirement. The real comparison isn't a single score. It's a task matrix. For routine email summarization in Outlook, Phi-3 Mini is good enough. For simple drafting and paraphrasing in Word, it's good enough. For meeting recap and action item extraction in Teams, it's good enough. For basic data description and formula assistance in Excel, it's good enough. For all of these tasks, the small model delivers acceptable quality at a fraction of the cost and latency. GPT-4 remains the right choice for the exceptions. Complex multi-document synthesis where nuance matters. Highly strategic documents where subtle misinterpretation carries risk, legal and compliance drafting where the model's broader knowledge base catches edge cases, cross-meeting analysis spanning 10 related transcripts where implicit patterns need to be detected. These are high-stakes, low-volume tasks where the premium model earns its keep. The smart architecture doesn't ask which model is better, it asks which model is appropriate, and the research is clear. For the high-volume, narrow, repeatable tasks that consume most of your Copilot budget, the small model is not a compromise, it's the correct specification. There's another benchmark dimension that matters for M365 specifically: context length. Phi 3.5 Mini supports up to 128,000 tokens of context, which is 4 times the 32,000 token limit of some GPT-4 configurations. For document-heavy workflows, analyzing a 50-page Word contract, summarizing a 100-message email thread, or querying across multiple Excel tabs, that longer context window means the SLM can ingest the full document in one pass rather than chunking it into smaller pieces and losing coherence. Combined with the much lower cost per token, this context advantage makes Phi-3 variants particularly well suited to the long document scenarios that are common in legal, compliance, and executive assistant workflows. The multimodal story also bears expanding. Phi-3 Vision's ability to read charts, diagrams, and text and images isn't just a technical curiosity. In Excel, users frequently take screenshots of pivot tables or charts and ask for analysis. In PowerPoint, presenters embed diagrams that contain as much information as the slide text. In Teams, whiteboard photos from hybrid meetings capture decisions that never made it into typed notes. A model that can interpret these visual elements and incorporate them into summaries, answers, or next step recommendations is doing work that a text-only model simply cannot do. And Phi-3 Vision does this at a scale and cost that makes it deployable for routine use rather than special occasions. And when you combine that specification with the economics of local deployment, the case becomes overwhelming. Cost and latency, the numbers nobody talks about. We've already touched on the pricing gap, but let's put it in deployment terms that an IT architect can take to a board meeting. Because the difference between cloud API pricing and self-hosted economics is where the real transformation happens. At cloud API rates, GPT-4 runs at approximately $30 per million tokens for input and $60 per million tokens for output. Flaw 3.5 mini runs at approximately 10 cents per million tokens for both input and output. That's a 300 to 1 difference on input and a 600 to 1 difference on output. If your organization processes 50 million tokens per month through Copilot, a conservative estimate for a mid-sized enterprise, the cloud API cost alone is $1,500 to $3,000 monthly at GPT-4 rates. At Flaw 3.5 mini rates, it's $5. But self-hosted economics are where the gap becomes transformative. When you deploy an SLM on your own Azure Local infrastructure or even commodity GPU hardware, the per-token marginal cost approaches zero. You're paying for the server, the electricity, and the operator time. The inference itself is effectively free at scale. Research on enterprise cost analysis notes that self-hosted SLM economics can widen the cost advantage to 100 times or more versus cloud LLM usage. For organizations processing at least 50 million tokens per month, on-premise deployment breaks even in months. The latency numbers are equally stark. When Flaw 3 Mini runs on local hardware or edge devices, it delivers first responses in 10 to 50 milliseconds. On an iPhone 14 with 4-bit quantization, it generates over 12 tokens per second using only 1.8 gigabytes of memory. Cloud-hosted GPT-4, by contrast, typically shows first token latency of 300 to 2000 milliseconds before generating any useful output. That gap is the difference between a tool that feels instant and a tool that feels delayed. In GPU environments, the throughput advantage compounds. Because SLMs are smaller, they can serve many more concurrent requests per GPU at a given latency target. For massive fan-out workloads like compliance scanning across a SharePoint tenant or always-on meeting summarization for every Teams call, this throughput difference means fewer GPUs, less infrastructure, and lower total cost of ownership. The research documents enterprise usage patterns that exploit these advantages. Tiered model routing, where the system starts with an SLM and escalates to a frontier model only when confidence or complexity demands it, routinely delivers 40 to 90% reductions in total LLM spend. Hybrid, draft, and refine patterns, where an SLM generates the first pass and a frontier model audits or refines a subset, capture most of the quality at a fraction of the cost. These aren't theoretical optimizations, they're deployment patterns that enterprises are already using, and they're patterns that become mandatory once Copilot moves from pilot to production. A pilot with 50 users can absorb frontier model costs. Production with 50,000 users cannot. The energy efficiency story adds another dimension to the cost discussion. Frontier models run on massive GPU clusters that consume enormous amounts of electricity. Every inference request carries a carbon footprint that, while small individually, aggregates into a significant environmental cost at enterprise scale. SLMs, by contrast, run on a fraction of the compute. A single modest GPU can serve hundreds of concurrent SLM requests with power consumption that wouldn't even register on a data center's cooling budget. For organizations with sustainability commitments or carbon reporting requirements, this efficiency isn't a side benefit, it's a measurable line item advantage, which brings us to the most important architectural insight of all. This isn't about replacing GPT-4 with Flaw 3, it's about building a system that knows which model to use for which task. The tiered architecture, not replacement but routing. The future of enterprise AI isn't one model. It's a portfolio of models orchestrated by a routing layer that matches each task to the smallest model that can handle it competently. Microsoft understands this. The company's March 2026 reorganization of Copilot into a single organization spanning experience platform applications and AI models was explicitly designed to enable this tiered future. The vision that emerges from Microsoft's documentation and community proposals is a layered assistant architecture. At the baseline tier, you get simple app-embedded chat, basic summaries, and straightforward drafting in Word, Outlook, and Teams. This is the free or low-cost tier, and it's exactly where SLMs shine. The tasks are narrow, the context is local, and the quality bar is high but not existential. At the context tier, Copilot gains memory and formatting intelligence. It learns your writing style, remembers your project context, and operates within a defined scope like a notebook focused on specific files. This tier requires more capability than the baseline, but still operates within bounded parameters that a small or medium SLM can handle. At the identity tier, Copilot becomes persistent across devices, retaining long-term memory of preferences, projects, and workflows. This is where the frontier model becomes more relevant, because cross-app reasoning and complex personalization demand broader capability. At the operator tier, Copilot acts as a full workflow manager, orchestrating multi-step processes across Word, Excel, PowerPoint, Outlook, and third-party systems. This is high-complexity, high-stakes automation that justifies frontier model investment. The business implication is clear. Different users need different tiers need different models, and charging everyone for the operator tier while delivering baseline tasks is exactly the structural flaw we're diagnosing. Microsoft's own product moves confirm this direction. Copilot notebooks, which allow users to create AI-powered notebooks focused on curated sets of files, represent a mid-tier capability that benefits from scoped, smaller models. Cross-app orchestration features where Copilot can schedule meetings in Outlook from Teams chat or push drafts directly into Mail show the platform evolving toward tiered intelligence rather than uniform capability. For enterprise architects, this means the design question changes. Instead of asking, which model should we standardize on, you ask, which model should handle which workload and how do we route between them? The answer is a tiered architecture where SLMs handle the bulk of routine traffic, and frontier models serve as escalation targets for complexity, ambiguity, and high-stakes output. This is the shift from model selection to model orchestration, and it's the shift that transforms Copilot from an expensive chat feature into a scalable, governable, cost-controlled AI platform. But orchestration doesn't just happen in the cloud. The real revolution is where these models run. The orchestration layer, how Copilot actually routes tasks. When most people imagine a tiered AI architecture, they picture a simple flowchart. Small tasks go left, complex tasks go right. But in reality, the orchestration layer is where the engineering gets interesting, because routing isn't just about task type. It's about confidence, risk, cost, latency, and data classification all at once. The standard Microsoft 365 Copilot architecture today follows a predictable pipeline. A user sends a prompt. The system enriches that prompt with context from the Microsoft graph. Emails, chats, files, calendar entries, meeting transcripts. Then a large language model generates a response. Post-processing checks refine the answer. Security trimming ensures the user only sees content they're authorized to access. And the response returns to the app. In a tiered architecture, that middle step, the LLM generation, becomes a routing decision. The system doesn't just hand every request to GPT-4. It first evaluates what the user is asking, what data is involved, and what quality threshold the task demands. Intent detection is the first filter. Is the user asking for a simple summary, a classification, a routine draft? Or are they asking for complex reasoning across multiple documents, creative writing, or strategic analysis? Simple intents route to SLMs immediately. Complex intents might still route to an SLM for an initial pass, with a frontier model serving as a verification layer. Policy-based routing adds the governance layer. Your organization might define that any request involving legal documents, HR records, or financial data must stay within your local infrastructure. These policies don't depend on what the user is asking. They depend on what data the prompt touches. If the Microsoft graph grounding pulls in files from a restricted SharePoint library, the routing layer directs the request to your locally hosted SLM, regardless of task complexity. Confidence scoring provides the feedback loop. When an SLM generates a response, the system can evaluate its own confidence. Low confidence outputs, ambiguous classification, uncertain summaries, requests that fall outside the model's training distribution can be escalated to a frontier model for refinement. This hybrid draft and refine pattern captures most of the cost and latency savings while preserving quality for edge cases. The research on enterprise routing architectures describes this as the increasingly dominant practical pattern. Organizations use SLMs for classification, extraction, routing, frequently asked questions, document tagging, and workflow automation. They reserve LLMs for open-ended customer interactions, complex reasoning, cross-document synthesis, creative drafting, and expert assistance. The boundary between these tiers isn't fixed. It's configurable based on your risk tolerance, your cost constraints, and your quality requirements. Microsoft's own technical positioning points in this direction. The company describes SLMs as the practical alternative where efficiency and device local deployment matter, while acknowledging that frontier models still handle the most demanding reasoning. The natural architecture that emerges from this positioning is exactly the tiered routing layer we're describing. For developers building on Azure, the tooling to implement this is already available. Azure AI Foundry provides the model catalog, evaluation tools, and deployment pipelines. Azure Arc extends these capabilities to on-premises and multi-cloud environments. And the RAG capabilities available as Azure Arc extensions give you end-to-end retrieval pipelines that can run entirely on local infrastructure, grounding SLM responses in your own documents without ever sending data to the public cloud. The key insight is that routing isn't an add-on, it's the architecture. Without it, you're either overpaying for frontier models on simple tasks, or you're underpowering complex tasks with small models. With it, you get the right model for every job and you maintain the governance controls that make enterprise deployment possible. There's a failure mode in routing architectures that deserves mention because it's the mistake most organizations make in their first implementation. They build the routing layer as a simple if-then-else system based on task type, and they discover that reality is messier than their categories. A request that looks like a simple summary might actually require reasoning over a legal document with subtle implications. A request that looks like complex analysis might turn out to be a routine extraction from a well-structured form. Static routing rules fail on these edge cases because they don't inspect the actual content or the actual data involved. The mature routing architectures solve this with dynamic evaluation. The system doesn't just look at the task type, it looks at the data classification, the document complexity, the user's role, the historical accuracy of each model on similar requests, and the real-time cost and latency constraints. This multi-factor routing is more complex to implement, but it's also more robust. It adapts to your organization's actual usage patterns rather than forcing your usage into predefined buckets. Another implementation detail that matters is request batching and caching. High-frequency tasks like document classification or entity extraction often receive identical or near-identical inputs repeatedly. A routing layer that caches SLM outputs for common requests can eliminate inference costs entirely for those cases. A routing layer that batches similar requests together can improve GPU utilization and reduce per-request latency. These optimizations are only available when you own the routing infrastructure rather than relying on a cloud provider's opaque scheduling. For Microsoft 365 specifically, the routing layer will likely emerge as part of the Copilot platform itself rather than as a custom build. Microsoft's tiered architecture vision, described in roadmap and community proposal documents, explicitly contemplates different capability tiers powered by different model families. As this platform matures, the routing decisions that today require custom engineering will become configurable policies in the admin console. Organizations that understand the routing concepts now will be ready to configure these policies effectively when they arrive. Organizations that don't will default to the most expensive tier for everything. But the most powerful form of this architecture doesn't just route between models in the cloud. It runs the small models exactly where your data already lives. Azure Local and the sovereign edge. Azure Local is Microsoft's answer to a question that regulated industries have been asking for years. Can we get the benefits of cloud AI without sending our data to the cloud? The answer is yes. But the implementation matters. Azure Local is first-party managed infrastructure that runs in your own data center or edge site, controlled through the same Azure management plane you already use. It's not a separate product with separate tooling. It's Azure, just located where you need it. That distinction is important because it means your existing operational skills, your existing policies, and your existing governance frameworks all apply without retraining your team. The platform supports 3 connectivity modes. Connected mode gives you full cloud integration with Azure services. Intermittently connected mode allows periodic synchronization for updates and telemetry. And fully disconnected mode, currently moving toward general availability, lets you run AI workloads in air-gapped or sovereignty-restricted environments with no network dependency on Microsoft's public cloud at all. For small language models, this deployment profile is transformative. A Phi 3 mini model running on Azure Local inside your facility delivers sub-50 millisecond responses to requests that never leave your network boundary. Your contracts, your patient records, your financial transactions, your classified documents, they can all be processed by AI without crossing a jurisdictional line. The integration stack is designed for this specifically. Azure Arc enables Kubernetes clusters on Azure Local to be managed with the same tools you use for cloud clusters. Azure AI Foundry Local brings model lifecycle management, evaluation, and monitoring to your on-premises environment. AKS Edge Essentials extends container orchestration to branch offices, factory floors, and remote sites. And the SLM sidecar pattern documented for Azure App Service but applicable anywhere lets you deploy a web application with its own embedded model in a single network boundary. Research on Azure Local use cases highlights the industries where this matters most. Manufacturing facilities use operator copilots for machinery troubleshooting, with SLMs interpreting natural language queries about machine states and maintenance logs without sending production data to the cloud. Energy and utility companies run anomaly detection and strategic planning models on infrastructure that stays within their operational technology perimeter. Government and defense organizations deploy fully disconnected clusters for policy assistance and secure knowledge bases in classified environments. The pattern across all of these deployments is the same. The data is too sensitive, too large, or too tightly coupled with on-premises systems to move to the cloud. The latency requirements are too strict to tolerate a round trip to a distant data center. The compliance requirements are too explicit to allow cross-border processing. And the SLM is exactly the right size to run on infrastructure they already control. Azure Local makes this practical by eliminating the operational gap between cloud AI and local AI. You're not cobbling together open source tools and praying they integrate. You're using Microsoft's first-party platform, Microsoft's model catalog, and Microsoft's security framework. The model just happens to be running in your building. The hardware requirements for running SLMs on Azure Local are also more accessible than many organizations assume. A dedicated NVIDIA GPU with 12 to 24 gigabytes of VRAM is sufficient for professional speed local inference of models like Phi 3 Mini and Phi 3 Small. For larger deployments, serving multiple concurrent users, a modest server with multiple GPUs can handle hundreds of simultaneous requests. And because SLMs don't require the massive GPU clusters that frontier models need, the capital expenditure is comparable to a mid-range database server rather than a supercomputer. The Azure Arc integration is what makes this manageable at scale. Your on-premises Kubernetes clusters are managed through the same Azure portal you use for cloud resources. Your DevOps team applies updates, monitors health, and scales capacity using the same Terraform templates and Azure CLI commands they already know. The learning curve is real, but it's incremental rather than revolutionary. You're extending existing skills rather than acquiring entirely new ones. But the sovereignty story doesn't end at your firewall. It extends to the legal jurisdictions that govern what you can and cannot do with your data. The EU data boundary and flex routing. If you're operating in the European Union, or if your organization serves EU customers, the data sovereignty discussion isn't abstract. It's governed by specific mechanisms with specific defaults that most administrators haven't fully reviewed. Microsoft's EU data boundary is a commitment that personal data for commercial and public sector customers in the EU and FDA will be stored and processed within that geographic region with a limited set of necessary exceptions. It's a genuine structural investment by Microsoft, completed for major cloud services in 2023 and 2024 and continuously refined since then, but the boundary has gaps. And in 2026, those gaps became active risks. Copilot Flex Routing is the most significant gap. As of April 2026, Microsoft enabled it by default for all EU and FTA tenants. When EU capacity is constrained, Copilot inference requests can be routed to data centers in the United States, Canada, or Australia. Microsoft states that customer data at rest remains in the EU, that requests are encrypted in transit, and that only limited pseudonymized data is stored outside the region for operational purposes. For many organizations, that explanation isn't sufficient. Processing personal data outside the EU triggers questions under the General Data Protection Regulation about international transfers, standard contractual clauses, and transfer impact assessments. If your National Data Protection Authority takes the view that inference processing constitutes data transfer, then flex routing may require a documented legal basis that your organization hasn't established. The mitigation is straightforward but requires action. Administrators can disable flex routing in the Microsoft 365 Admin Center under Copilot settings and data location, but the default is on. And many organizations deploy Copilot without reviewing the specific toggle, assuming that the EU data boundary protects them comprehensively. The Anthropic model integration creates a second gap that flex routing controls do not address. When Copilot uses Claude models for certain capabilities, those requests are processed on AWS infrastructure in the United States. No setting in your Microsoft 365 Admin Center changes that location. Microsoft's enterprise data protections still apply. No model training on your data, encryption throughout, but the jurisdictional location of processing is fixed. For organizations where strict EU residency is mandatory, the only mitigation is to ensure Anthropic models remain disabled. Then there's Bing-connected web search. Copilot features that rely on web search route queries through services outside your tenant, typically hosted in the United States. Microsoft asserts that search queries aren't stored or used to profile your tenant, but this is a processing activity outside your boundary that your privacy documentation may not cover. Microsoft is expanding in-country and regional inferencing to address these concerns. By the end of 2026, the company plans to offer in-country Copilot processing in 15 countries, including Germany, Italy, Poland, Spain, Sweden, Switzerland, and others. For the EU, this takes the form of regional inferencing aligned with the EU data boundary commitments. As this capacity expands, the pressure to use flex routing decreases, but the toggle remains. The option to route outside the EU remains, and the compliance risk remains until you explicitly configure it away. This is why local deployment on Azure Local isn't just a performance optimization for EU organizations, it's a compliance architecture. When your SLM runs in your Frankfurt data center, processing your German employee documents, no flex routing toggle matters, no Anthropic model location matters, no Bing web search routing matters. The data never leaves the building. The jurisdiction is yours. The control is yours. For data protection officers, this transforms the risk conversation from trust Microsoft's configuration to verify our own infrastructure. It's a different level of assurance, and for organizations operating under sectoral regulations like the Digital Operational Resilience Act for Financial Services or national health privacy laws, that level of assurance can be the difference between approved deployment and legal exposure. So the question becomes, what does this look like specifically for the tools your employees use every day? M365. Local AI on your terms. Microsoft 365. Local is the emerging scenario that brings together everything we've discussed so far. It's the intersection of Azure Local infrastructure, small language models, and your existing Microsoft 365 content, operating under your governance rather than Microsoft's cloud defaults. The concept is straightforward. Your enterprise content lives in Microsoft 365. SharePoint document libraries, Exchange mailboxes, Teams chat histories, OneDrive files. Traditionally, when Copilot processes that content, it sends requests to Microsoft's cloud AI services. With M365 local scenarios, the content stays in your local environment, and the AI processing happens on your Azure Local cluster using SLMs that you control. This isn't full offline Microsoft 365. Your tenant still synchronizes with Microsoft's cloud for identity, licensing, and core services, but the AI layer, the summarization, the classification, the drafting, the extraction, runs locally. For organizations that have already invested in hybrid Microsoft 365 architectures, this is a natural extension rather than a disruptive replacement. The scenarios that M365 Local enables are exactly the high-frequency, low-complexity tasks we've been discussing. An employee opens Outlook and asks Copilot to summarize an email thread. Instead of that request traveling to a Microsoft data center for processing, it hits your local Phi-3 model running on Azure Local inside your facility. The response returns in under 100 milliseconds. The email content never leaves your network. The summary is generated, delivered, and forgotten without a single byte crossing your perimeter. In Teams, a manager asks for action items from a meeting transcript. The transcript is already stored in your local SharePoint. The SLM extracts tasks, assigns owners, and formats the output. There is no cloud round trip, no flex routing concern, and no transfer assessment required. For Word and Excel, the pattern repeats. Document summarization, style transformation, simple formula explanation, and data description all become local operations. The heavy creative writing, complex multi-sheet analysis, and strategic synthesis still route to frontier models in the cloud. But the routine work, the 80% of requests that make up 20% of the cognitive load, stays local. Microsoft's documentation on on-device and local deployment positions this as a strategic direction rather than a fringe feature. The company describes a hybrid AI approach where cloud-hosted Copilot handles large-scale reasoning and smaller models run closer to the user for speed, privacy, and offline resilience. While the specific product boundaries and licensing models for M365 Local are still emerging, the architectural direction is clear. Microsoft is building toward a world where not every Copilot request needs the cloud. For IT leaders, the practical implication is that future M365 AI controls won't just manage cloud Copilot policies. They'll need to manage device eligibility, model selection, local data handling, and endpoint governance. The admin console expands from cloud toggles to hybrid orchestration, and the skill set required shifts from SaaS administration to hybrid AI platform management. The offline resilience story deserves more attention than it typically gets. Most cloud-first AI conversations assume reliable, high-bandwidth connectivity. But enterprise reality is messier. Branch offices with DSL connections, manufacturing plants in remote locations, ships, planes, and field stations where connectivity is intermittent or non-existent. Hospitals that maintain isolated networks for critical systems. In all of these environments, cloud-dependent AI is either frustratingly slow or completely non-functional. Local SLMs change this fundamentally. A model running on an edge device or local server continues to operate when the one is down. An engineer troubleshooting equipment in a basement can still query the maintenance Copilot. A doctor in an isolated clinic can still summarize patient notes. A soldier in a forward operating base can still access the policy assistant. The research on Azure Local explicitly highlights this resilience as a core value proposition, noting that local inference enables real-time or near real-time AI, even when one links are slow or unavailable. For Microsoft 365 specifically, the offline scenario is particularly relevant because M365 itself has hybrid capabilities. Organizations running Exchange Server in hybrid mode or SharePoint Server with cloud synchronization already manage the complexity of split workloads. Adding local AI processing to this stack is a natural extension rather than a radical departure. The content is already in both places. The AI just needs to run where the content lives. Microsoft's documentation frames this as a strategic direction, describing SLMs as essential for scenarios where limited computing power, low latency, or keeping costs down is critical. The company positions on-device and local deployment not as a downgrade from cloud AI, but as a necessary complement that extends AI capability to places the cloud can't reach. And for organizations that have already invested in hybrid Microsoft infrastructure, the operational model is familiar. It's just a new workload on existing infrastructure. But this isn't science fiction. Organizations are already doing it. Real-world deployment patterns. The research on Azure Local and SLM deployments documents specific industries and use cases where this architecture is already in production. These aren't pilot projects, they're operational systems handling real workloads. In manufacturing, operator copilots interpret natural language queries about machine states, procedures, and alarms. An operator on the plant floor asks why a particular line is showing a warning light. The SLM running on an edge cluster inside the facility, queries local maintenance logs and procedural documents, then returns a diagnosis and recommended next steps. The response arrives in under a second. The production data never leaves the plant network. And when the one connection is down, the Copilot keeps working because it doesn't need one. In regulated environments like government and defense, policy assistants answer staff queries against internal regulatory manuals and legal frameworks. The SLM is fine-tuned on the organization's own documents. The RAG pipeline indexes classified or sensitive documentation stored on sovereign infrastructure. And because the entire stack runs on Azure Local in disconnected mode, the system meets air-gap requirements without sacrificing modern AI capabilities. In financial services, local SLMs analyze transaction histories and customer profiles for pattern detection and risk assessment. The data is subject to strict localization laws that prohibit cloud processing. The SLM provides analytical capability that would otherwise require manual review or expensive on-premise traditional software. And the organization maintains full control over model versions, logging, and data retention. Healthcare organizations use local SLMs for clinical note summarization, radiology report processing, and patient record analysis. Patient privacy laws in most jurisdictions make cloud AI processing legally complex or impossible for identifiable health records. A locally deployed model, running on hospital-controlled infrastructure, delivers the productivity benefits without the compliance risk. The common pattern across all of these deployments is hybrid search and retrieval. The Azure Arc extension for RAG provides end-to-end pipelines for data ingestion, vector index creation, and retrieval APIs that integrate with language models. It works with on-premises and multi-cloud data sources, and it's designed specifically for the data sovereignty, latency reduction, and compliance requirements that drive local deployment decisions. For horizontal enterprise use cases, the patterns are equally practical. Knowledge Copilots index wikis, file shares, CRM records, and support tickets that must remain on-premises. Project and proposal generation tools create first drafts grounded in past deliverables and internal templates stored on local file servers. Change management and training bots ingest HR and IT documentation locally, giving staff conversational access to policies without requiring them to search through multiple portals. These deployments share three characteristics. They run on infrastructure the organization controls, they process data that never leaves the organization's jurisdiction, and they use small language models because the tasks are narrow enough that a small model is not just sufficient but optimal. The retail and hospitality sector presents another compelling pattern. In-store associate copilots run on small edge clusters at each location, assisting staff with product information, inventory queries, and policy questions using store-specific data and regional promotions. Customer-facing kiosks use natural language interaction to guide shoppers, with the privacy benefit that no conversation logs leave the device. Facilities management bots interpret building sensor data and maintenance logs to answer operator questions about alerts and historical behaviors. All of these use cases share a common constraint. The branch or site has limited IT support, intermittent connectivity, and a requirement that sensitive customer or operational data stays on site. The SLM sidecar pattern, originally documented for Azure App Service, has become a standard deployment template across these scenarios. An application container and its embedded model run in the same pod or service plan, communicating through internal network calls that never cross a perimeter. For line-of-business applications that need AI augmentation, form automation, document understanding, context-aware search across legacy ERP systems, this pattern delivers capability without replatforming the entire system. The SLM becomes an internal API endpoint that the existing application calls, just like it would call a database or a caching layer. The operational complexity is real. Running AI on-premises requires capacity planning, hardware lifecycle management, Kubernetes operations, and security hardening. Azure Local mitigates much of this through managed aspects, but the organization still manages the physical environment. The skills required span DevOps, MLOps, and traditional IT infrastructure. For many teams, this is a learning curve. But the alternative, running everything through cloud frontier models, is increasingly untenable for organizations with strict data controls, unpredictable costs, or latency requirements. The question isn't whether local deployment is more complex, it's whether the benefits outweigh that complexity. And for the use cases we're seeing in production, the answer is increasingly yes, which brings us to the last piece of the architecture. Because deploying models locally doesn't eliminate your security responsibilities, it changes them. The security and compliance architecture. When you move AI processing from Microsoft's cloud to your own infrastructure, the security model doesn't get simpler, it gets different. You trade reliance on Microsoft's security operations for direct control over your own. And that trade is only valuable if you implement the controls correctly. The first control is data classification and routing. Not all data is equally sensitive. Your public marketing materials can probably process through cloud AI without concern. Your board minutes, your merger documents, your patient records, and your classified contracts cannot. A tiered data classification system, public, internal, sensitive, highly sensitive, drives the routing policy. Highly sensitive data processes exclusively on local SLMs. Sensitive data might process on local SLMs with optional cloud escalation for specific tasks. Public and internal data can use cloud services where latency or cost benefits exist. The second control is encryption and access management. Data at rest and in transit around the SLM environment must be encrypted. Access to the model endpoints must be authenticated through your existing identity system, not left as anonymous APIs on your internal network. And the principle of least privilege applies to both human users and service accounts that call the model. The third control is logging, retention, and audit. Local deployment means you own the logs. You determine how long prompt histories are retained. You control whether outputs are stored for quality review. And you integrate SLM usage into your existing data governance processes, documenting which data the model accesses, which versions are deployed, and how evaluation artifacts are maintained. Microsoft's own security and compliance guidance for SLMs emphasizes responsible AI post-training. The 5.3 technical report documents substantial safety improvements across multiple benchmark categories after safety tuning, and Azure AI Content Safety provides filtering and monitoring tools that can be deployed alongside your local models. The research on data sovereignty best practices frames this as a foundational requirement. Organizations need robust encryption, pseudonymization where appropriate, regular audits, and clear data processing agreements with any external providers. When you're running your own SLM, the external provider is gone, but the governance requirement remains. You're now the provider, and your auditors will hold you to the same standards they would hold Microsoft. For organizations that already operate regulated on-premises systems, this isn't a new challenge. It's an extension of existing practices. The SLM becomes another workload in your compliance scope. The novelty is that this workload can now deliver AI capabilities that previously required cloud services. The governance is familiar, the capability is new. There's an additional layer of security consideration specific to SLMs that doesn't get enough attention. Because small models can be fine-tuned and customized more easily than frontier models, they also present a different attack surface. A poisoned training dataset, whether introduced maliciously or through poor data curation, can embed backdoors or biases that are harder to detect in a smaller parameter space. An attacker with access to your fine-tuning pipeline can potentially influence model behavior in ways that wouldn't be feasible with a trillion-parameter model hosted by a major cloud provider. This doesn't mean SLMs are less secure. It means the security model is different. With frontier models, you're outsourcing security to Microsoft, OpenAI, or Anthropic. They control the training data, the model weights, the update cadence, and the safety filters. With local SLMs, you own all of those responsibilities. The trade-off is control for effort. You get complete visibility into what the model was trained on, how it's behaving, and what it's producing, but you also need the internal capability to verify and validate those things. The research on Azure SLM deployment security emphasizes this point. Best practices include encrypting data at rest and in transit, applying strong access control and authentication to local model endpoints, configuring logging and retention consistent with local laws, and integrating SLM usage into existing data governance processes. These aren't optional extras, they're foundational requirements for any production deployment. Model versioning is another critical control. When you deploy an SLM locally, you decide when to update it. You can test a new version in a staging environment before promoting it to production. You can roll back if the new version produces different or worse output. You can maintain multiple versions for different use cases or departments. This level of control is impossible with cloud API models, where the provider can update the model weights at any time without notifying you, and where model versions are often just API endpoint aliases that point to whatever the provider currently considers the best model. For regulated industries that require reproducibility and auditability, this control is essential. A financial services firm that uses an AI model to flag suspicious transactions needs to be able to reproduce the model's decision 6 months later during an audit. If the model has been silently updated by the cloud provider, reproducibility is impossible. With a locally deployed version-controlled SLM, the firm can maintain the exact model weights, the exact inference code, and the exact input-output pairs for as long as regulatory requirements demand. So we've diagnosed the flaw, we've explored the fix, we've looked at the architecture, the deployment patterns, and the security model. The remaining question is how you put this together into a strategy your organization can actually execute. Building your model mixture strategy. If you take one thing from this deep dive, take this. The goal isn't to replace GPT-4 with Phi 3. The goal is to stop using a single model for every task and instead build a portfolio where each model handles the work it was designed for. That's the model mixture strategy, and it's how you turn Copilot from a cost center into a competitive advantage. The first step is establishing your performance ceiling. Before you can decide which tasks belong to small models, you need to know what good looks like. Run your existing high-value tasks through GPT-4 or GPT-4o. Document the output quality, the latency, the cost per task, and the user satisfaction. This isn't wasted spend. It's your baseline. It tells you what the premium tier delivers. and it gives you a target to match when you start routing work to smaller models. The second step is identifying your high-volume, repeatable workflows. These are the tasks your employees perform dozens or hundreds of times per day. Email summarization, meeting action item extraction, document classification, routine drafting and replies, simple data extraction from structured forms. These tasks have predictable inputs, bounded outputs, and consistent quality requirements. They are perfect candidates for SLM migration because the patterns are stable and the volume is high. The research on enterprise cost analysis provides a clear framework for this identification process. Look for workflows that are narrow, repetitive, and high throughput. Tasks where good enough accuracy is sufficient because outputs are reviewed, validated, or low stakes. Tasks where latency matters because users interact with them in real time. And tasks where data sensitivity is high because keeping processing local reduces compliance risk. The third step is piloting with real production data. This is where most organizations go wrong. They test SLMs on synthetic benchmarks or demo datasets, get mediocre results, and conclude that small models don't work. But synthetic data doesn't capture your document formats, your terminology, your templates, or your edge cases. A Phi-3 model tested on generic summarization benchmarks will perform differently than the same model tested on your actual email threads. Run a controlled pilot, select one workflow, route 50% of requests to the SLM and 50% to the incumbent frontier model. Measure accuracy against a human-reviewed gold standard, measure latency end-to-end, measure cost per 1,000 requests, and measure user adoption. Are users still engaging with the SLM-powered version, or are they abandoning it for manual workarounds? The research on Phi-3 performance specifically highlights why production data matters. For tasks involving reasoning over user-provided content, summarizing a meeting transcript, extracting action items from an email thread, Phi-3's knowledge limitations matter less because the information is in the prompt, not the model's training weights. But for tasks requiring general world knowledge or specialized domain knowledge not present in the document, the small model may struggle. You won't know which category your task falls into until you test it with your own data. The fourth step is building your routing layer. This is the engineering heart of the model mixture strategy. You need a classification or routing mechanism that evaluates each incoming request and directs it to the appropriate model tier. Policy-based routing is the simplest approach. Hard rules based on data classification, task type, or user role. If the request involves legal documents, route to local SLM. If the request is a simple summary, route to local SLM. If the request involves creative writing or strategic analysis, route to cloud frontier model. These rules are transparent, auditable, and easy to implement, but they're rigid. They don't adapt to task complexity that falls outside predefined categories. Confidence-based routing is more sophisticated. The SLM generates a response and simultaneously produces a confidence score. Low confidence triggers automatic escalation to the frontier model. This approach captures edge cases that policy rules miss, but it requires the SLM to be well calibrated on your specific tasks. A model that is overconfident on generic benchmarks might be underconfident on your proprietary document formats, or vice versa. Learned routing is the most advanced approach. You train a lightweight classifier, sometimes just a few hundred examples, to predict which model will produce the best output for a given input. The classifier learns from your actual production feedback, where human reviewers or automated metrics score outputs from both the SLM and the frontier model. Over time, the classifier becomes increasingly accurate at matching tasks to models, maximizing quality while minimizing cost. The research on enterprise routing architectures documents all three approaches in production. Organizations typically start with policy-based routing because it's implementable in weeks. They add confidence scoring once the SLM is tuned on their data, and they move to learned routing only after they have enough production feedback to train the classifier effectively. The progression from simple to sophisticated mirrors how most enterprise technology adoption works. The fifth step is department-based tiering. Not every department in your organization has the same risk tolerance, data sensitivity, or compliance requirements. Your legal team and your finance team probably need stricter controls than your marketing team. Your R&D division may have intellectual property constraints that your customer service division doesn't. Design your model mixture strategy with these differences in mind. For high-risk departments, mandate local SLM processing with explicit frontier model escalation only for approved use cases. For medium-risk departments, allow hybrid routing with automatic escalation. For low-risk departments, permit broader cloud model usage while still routing routine tasks to SLMs for cost control. The EU data boundary discussion we covered earlier feeds directly into this tiering. Organizations operating under strict EU residency requirements should default every department to EU-only processing, with local SLMs as the standard and cloud frontier models as the exception. Organizations with more flexible requirements can allow broader cloud usage for departments that don't handle personal data or regulated content. The sixth step is defining your fallback and error handling. No routing system is perfect. There will be times when the SLM produces output that is factually wrong, contextually inappropriate, or simply unhelpful. Your architecture needs graceful degradation. Common patterns include automatic frontier model fallback for low-confidence outputs, human-in-the-loop review for high-stakes tasks, and output logging for continuous quality monitoring. The research on hybrid architectures emphasizes that keeping a frontier model fallback is essential. The SLM handles the bulk traffic, the frontier model catches the exceptions, and the human reviewers catch the cases that neither model handles correctly. The seventh step is continuous evaluation and iteration. Model performance isn't static. Your document formats change. Your employee behavior changes. The models themselves improve through updates and new releases. A model mixture strategy that works in Q1 may need adjustment by Q3. Set up evaluation pipelines that regularly sample outputs from each model tier. Compare SLM outputs against frontier model outputs on identical inputs. Track cost per task, latency per task, and user satisfaction scores. Monitor for drift, situations where the SLM's performance degrades on tasks it previously handled well, and maintain a backlog of tasks to migrate from frontier to SLM as the small models improve. Microsoft's own roadmap supports this iterative approach. The Phi family continues to evolve, with Phi 3.5 variants already showing substantial improvements over the initial Phi 3 release. Azure AI Foundry Local provides model evaluation and monitoring tools that work on-premises as well as in the cloud, and the company's 5-year mission to build its own frontier models suggests that the entire model portfolio will become more capable, more efficient, and more tightly integrated over time. The final point on strategy is organizational, not technical. Someone in your organization needs to own the model mixture. Not the AI steering committee in aggregate, but a specific team or individual with the authority to define routing policies, approve model deployments, review evaluation metrics, and adjust the architecture based on results. Without clear ownership, the tiered system becomes a committee consensus that defaults to the safest option, which usually means routing everything through the most capable and most expensive model. There's also a cultural dimension to this ownership that most technology strategies overlook. Your employees have already formed mental models about AI capability. They assume that the best model is the biggest one. They may resist a tiered architecture because it feels like a downgrade. Why am I getting the cheap model while the executives get the good one? This perception can undermine adoption if you don't manage it explicitly. The way to manage it is through transparency and demonstration, not assertion. Show users the latency difference. Let them experience the instant response of a local SLM side by side with the delayed response of a cloud frontier model. Explain that the routing isn't about their importance, it's about the task's requirements. A routine summary doesn't need a trillion parameters any more than a commute to the grocery store needs a Formula One car. The right tool for the job is the smart choice, not the expensive choice. Employee education also matters for data handling. When users understand that their legal documents stay local because of compliance requirements, they're more likely to accept routing decisions that might otherwise feel arbitrary. When they see that their personal data isn't being sent to another continent for processing, they develop trust in the system. That trust translates to adoption, and adoption translates to the ROI that justifies the entire program. The research on enterprise AI adoption patterns confirms this cultural dimension. Organizations that treat AI deployment as purely a technical rollout, infrastructure, licensing, feature enablement, see lower adoption than organizations that invest in change management, user training, and transparent communication about how the system works. The model mixture strategy is no exception. If your employees don't understand why they're getting a small model for one task and a large model for another, they'll assume the system is broken or that they're being shortchanged. But that ownership structure matters because the next 24 months will bring changes that require active decisions, not passive observation. The 24-month roadmap. Enterprise technology roadmaps are usually fiction. Vendors promise capabilities that slip by quarters or years. Regulatory requirements change mid-cycle. Budget approvals lag behind technical readiness. But the trajectory of SLM integration into the Microsoft ecosystem is clear enough that you can plan with reasonable confidence, provided you understand what's committed, what's probable, and what's speculative. In the second half of 2026, Microsoft's immediate priorities are expanding the infrastructure that makes local deployment practical. Azure Local is moving toward broader general availability, with specific emphasis on the disconnected deployment mode for air-gapped and sovereignty-restricted environments. This matters because right now many organizations can pilot local SLMs but can't fully operationalize them at scale without supported managed infrastructure. General availability changes that equation from experimental to production-ready. The in-country and regional inferencing rollout continues through late 2026. By the end of the year, Microsoft plans to offer in-country Copilot processing in 15 countries, including regional inferencing aligned to the EU data boundary for EU and EFTA tenants. As this capacity comes online, the pressure on flex routing decreases. Organizations that have disabled flex routing for compliance reasons may be able to re-enable it selectively, confident that routine traffic stays within their region. For EU organizations, this is a significant milestone. It means that even cloud-hosted Copilot processing can increasingly stay within the EU, reducing the gap between cloud convenience and local sovereignty. But the fundamental architectural choice remains. Cloud processing in the EU is better than cloud processing outside the EU. Local processing in your own facility is better still, because you control the hardware, the logs, and the data retention policy. The in-country inferencing rollout also creates an interesting intermediate option for organizations that aren't ready for full Azure Local deployment. If Microsoft offers EU-based inferencing for standard Copilot tasks, an organization can keep routine processing in-region without managing local infrastructure. The high-sensitivity tasks can still route to Azure Local SLMs, and only the most complex cross-jurisdictional tasks need to touch models outside the EU. This layered approach, local for highest sensitivity, regional for moderate sensitivity, global for lowest sensitivity, gives organizations a graduated path rather than a binary choice. The Phi model family will continue to see incremental improvements. Phi 3.5 variants are already demonstrating performance that approaches GPT-4o Mini on many benchmarks. The mixture of experts architecture in Phi 3.5 MOE shows a path forward where small models can deliver larger model capability through smarter routing of internal computation rather than brute parameter scaling. And Microsoft's investment in its own frontier models, led by Mustafa Suleyman's 5-year mission, suggests that the entire model stack, small, medium, and large, will become more capable and more cost-efficient. The multi-model ecosystem is also expanding. Microsoft has already integrated Anthropic's Claude models into parts of the Copilot ecosystem through Copilot Studio. The company maintains a reported $250 billion compute partnership with OpenAI. And Microsoft's own MRI voice, MRI image, and reasoning-focused models add specialized capabilities for speech, vision, and complex workloads. This portfolio approach means that in 2027, your routing decisions won't just be between Phi 3 and GPT-4. They'll be between a dozen models optimized for specific modalities and tasks. For M365 specifically, the integration timeline points toward deeper embedding of SLM-powered features. Copilot notebooks, which allow scoped intelligence over curated file sets, represent a mid-tier capability that benefits from local processing. Cross-app orchestration, where Copilot moves seamlessly between Outlook, Teams, Word, and Excel, generates more requests that benefit from low-latency local handling. And persistent Copilot identity, a long-term memory of user preferences, writing style, and project context, will require both cloud synchronization and local caching to deliver responsive, personalized experiences. The Build 2026 emphasis on proving Copilot value in real production workflows rather than demos signals a maturation of the platform. Microsoft knows that enterprise adoption in 2026 and 2027 depends on demonstrated ROI, not potential capability. That pressure works in favor of SLM adoption because SLMs make the ROI math work for the bulk of routine tasks. A Copilot deployment that costs 5 times less per interaction and responds 10 times faster is easier to justify to a CFO than one that depends on frontier models for everything. For your organization's planning, this means 3 concrete priorities over the next 24 months. First, establish your evaluation infrastructure. Whether you use Azure AI Foundry, Azure AI Studio, or custom tooling, you need the ability to benchmark models against your own data, measure cost and latency in production-like conditions, and compare outputs side by side. This infrastructure is a prerequisite for every subsequent decision. Second, build your pilot program. Select 2 to 3 high-volume, low-risk workflows and run them through a model mixture architecture. Document the results. Calculate the actual savings, the actual latency improvements, and the actual quality deltas. Use these pilots to build organizational confidence and secure budget for broader rollout. Third, develop your governance framework. Define your data classification rules, your routing policies, your fallback procedures, and your audit requirements before you scale. It's much easier to design governance for 1,000 users than to retrofit it for 10,000. And regulators, auditors, and internal risk committees will ask for documentation that is far easier to produce proactively than reactively. The organizations that get ahead of this curve in 2026 and 2027 will have a structural advantage. Their Copilot deployments will be cheaper, faster, and more compliant than competitors still routing everything through premium cloud models. Their IT teams will have the skills, the tooling, and the organizational buy-in to iterate as the model landscape evolves. And their data will remain under their control regardless of how cloud provider policies change. The organizations that wait will find themselves chasing a moving target. Copilot costs will keep rising as usage scales, latency complaints will accumulate, compliance audits will reveal gaps they didn't know existed. And when they finally decide to act, they'll be starting from behind. There's a competitive dynamic here that most strategic plans miss. The early adopters of model mixture architectures aren't just saving money, they're building organizational capability that compounds over time. Their teams learn how to evaluate models, how to fine-tune on proprietary data, how to deploy on hybrid infrastructure, and how to govern multi-model systems. When the next generation of models arrives, whether it's 5.4, a Microsoft-built frontier model, or something entirely new, these organizations can adopt it faster because their pipeline is already built. Their competitors, still running everything through a single cloud API, have to start from scratch every time the landscape shifts. This capability advantage is particularly relevant given Microsoft's 5-year frontier model mission. When Microsoft delivers its own general-purpose frontier model, the economics of the Copilot stack will change again. A company that already runs a tiered architecture will be able to swap in the new model at the high tier without disrupting the SLM-powered bulk traffic. A company running frontier only will face yet another cost and complexity spike as they try to integrate yet another premium model. The skills gap is another factor that favors early action. Right now, there's a shortage of engineers who understand both traditional IT infrastructure and modern AI deployment. The people who can run Kubernetes, manage GPU clusters, fine-tune language models, and implement retrieval-augmented generation pipelines are in high demand and short supply. Organizations that start building this capability in 2026 will have access to a larger talent pool and more time to train internal staff. Organizations that wait until 2028 will be competing for the same scarce talent against everyone else who finally woke up to the need. Azure Local and the associated hybrid tooling are also evolving rapidly. Each quarter brings new features, better integration, and simplified deployment patterns. Organizations that start early can grow with the platform, adopting new capabilities as they mature. Organizations that start late will face a steeper learning curve because the platform will be more capable but also more complex. The window for relatively simple entry is now. Which brings us to the bottom line. Because all of this architecture, strategy, and planning is only worthwhile if it delivers measurable value. The real ROI of SLMs in enterprise, return on investment for AI initiatives, is notoriously difficult to calculate. Vendors sell potential, finance teams demand proof, and the gap between pilot success and production value is where most AI projects die. So let's be specific about what small language models actually deliver in terms that survive a board-level review. The most direct ROI is cost reduction. Organizations running tiered architectures with SLMs, handling routine traffic report, 40 to 90% reductions in total LLM spend compared to frontier-only designs. That isn't a minor optimization. For an enterprise spending 6 or 7 figures annually on AI inference, a 50% reduction is material. It frees budget for other initiatives. It extends the runway of AI programs that might otherwise face cuts. And it transforms the conversation from AI is expensive to AI is efficient. To make this concrete, consider a mid-market enterprise with 1,000 Copilot users. If each user generates an average of 20 requests per day, and each request consumes roughly 2,000 tokens of combined input and output, the monthly token volume is 40 million. At GPT-4o blended rates, that's approximately $160,000 per year in inference costs alone. Switching routine tasks to an SLM at 1/10 the cost reduces that line item to $16,000. The $144,000 difference pays for an additional full-time AI infrastructure engineer, a local GPU server, and the operational tooling to manage the hybrid architecture, with budget left over. The research on enterprise cost analysis frames this as a shift in AI adoption maturity. Early pilots favor large models because they minimize engineering effort and maximize capability. But production systems increasingly optimize for unit economics, latency, and governance. The market is moving towards specialized model portfolios rather than single universal models, and the organizations that make this shift early capture the cost advantage before their competitors even recognize the option exists. Latency reduction delivers a different kind of ROI. User adoption. A Copilot feature that responds in under 100 milliseconds feels like a native part of the application. A feature that takes 2 seconds feels like a separate system. The difference in user behavior is dramatic. Employees integrate fast tools into their muscle memory. They avoid slow tools after the third frustrating delay. And adoption metrics are what finance committees look at when deciding whether to renew licenses or expand deployment. The research on latency benchmarks makes the user experience case explicitly. SLMs on edge hardware deliver 10 to 50 millisecond responses. Cloud LLMs deliver 300 to 2,000 milliseconds. That isn't a technical detail that only engineers care about. It's the difference between a tool that becomes habit and a tool that becomes shelfware. Sovereignty and compliance ROI is harder to quantify but equally real. Avoiding a regulatory fine or a data breach is worth more than any cost optimization. Enabling AI capabilities in jurisdictions where cloud processing is legally restricted opens markets and use cases that would otherwise remain blocked. And the internal confidence that comes from knowing your data never left your facility is a qualitative benefit that shows up in faster decision-making, broader deployment approvals, and reduced risk committee friction. The EU data boundary research we reviewed earlier highlights this in concrete terms. Organizations that disable flex routing, block anthropic models, and route sensitive processing to local infrastructure avoid international transfer assessments, legal review cycles, and the operational overhead of managing cross-border data flows. For organizations in regulated sectors like finance, healthcare, and government, this isn't a nice to have, it's a prerequisite for operation. But there's a hidden ROI that most cost analyses miss: developer velocity and shadow IT reduction. When your official AI platform is slow, expensive, and hard to govern, employees find alternatives. They use personal accounts with public AI services. They copy sensitive documents into unauthorized tools because the approved tool is too painful to use. They build departmental workarounds that bypass IT entirely. This shadow AI usage is invisible to cost reports and compliance audits until it becomes a breach or a leak. A fast, affordable, well-governed model mixture architecture brings that usage back into the light. Employees use the official platform because it's the best option, not because it's the only permitted option. IT maintains visibility and control, and the organization captures the productivity benefits without the compliance risks. Microsoft's own positioning of SLM supports this interpretation. The company describes small models as ideal for scenarios where efficiency and device local deployment matter, and emphasizes their role in hybrid architectures alongside cloud-delivered Copilot. This isn't Microsoft hedging its bets, it's Microsoft acknowledging that the future of enterprise AI is distributed, tiered, and context-sensitive. The total ROI picture combines all of these factors: direct cost savings on inference, indirect savings from higher adoption and lower support overhead, risk reduction from local processing and stronger governance, and strategic positioning from having an AI architecture that scales with usage rather than choking on it. There's one more ROI dimension that deserves attention: the environmental argument. Large language models consume enormous amounts of electricity. A single frontier model inference request might use enough energy to power a light bulb for an hour. When that request is multiplied by millions of daily interactions across thousands of enterprises, the aggregate environmental impact is significant. Small language models, by virtue of their efficient architecture, use a fraction of the energy per request. For organizations with carbon reduction commitments, or for organizations in jurisdictions with emissions reporting requirements, the energy efficiency of SLMs isn't a side benefit. It's a compliance and reputation consideration. The research on enterprise AI cost drivers notes that SLMs require fewer resources than LLMs, reducing compute and energy consumption while still providing high utility for domain-specific tasks. In an era where data center emissions are under increasing scrutiny from regulators, investors, and customers, this efficiency advantage will only grow in importance. A sustainability officer asking about the carbon footprint of your AI deployment will find a much better story to tell with SLMs handling 80% of the workload. For the IT leader pitching this to the board, the framing is straightforward. We can continue paying premium prices for every AI request, watching adoption plateau because users won't wait, managing an expanding compliance surface area as cloud routing options multiply, and consuming energy at rates that undermine our sustainability commitments. Or we can build a tiered architecture that matches the right model to each task, delivering faster responses at lower cost with stronger data control and reduced environmental impact. The technology exists, the benchmarks exist, and the deployment patterns exist. The only question is whether we lead the transition or follow it. And that's exactly where this conversation lands, because the flaw we've been diagnosing isn't a product bug, it's an architectural assumption, and assumptions are choices. The organizations that thrive in the next phase of enterprise AI won't be the ones with the biggest models. They'll be the ones with the smartest architecture. A tiered system where small language models handle the routine work locally, cheaply, and privately, while frontier models stay in reserve for the exceptions that actually need them. That's the SLM revolution, and it's not coming. It's already here. Every day you wait, your Copilot costs climb, your compliance surface expands, and your users grow more frustrated with tools that promise intelligence but deliver delays. The architecture to fix this exists, the models exist, and the deployment patterns exist. The only missing piece is the decision to stop accepting a broken assumption and start building a smarter system. If this changed how you think about Copilot and AI architecture, follow me, Mirko Peters, on LinkedIn for more deep dives on Microsoft 365, Azure, and the systems behind modern work.